Alright, hi. Hi. Technical Manual 53015. Technical Manual. Firefighting, Rescue Procedures, and Theater Operation, Headquarters Department, Army, 1971. Chapter 3. Chapter 3. Characteristics, Chemistry, and Physics of Fire. Through 1. The number of fires caused by unnatural reactions is minimum in relation to those caused by carelessness of men and apathy of acquiring and using information available for the on characteristics, chemistry, and physics of fire. The knowledge of principles of fire also helps the firefighter to extinguish those fires that he fails to prevent. 3.2. The nature of the fire. The process of the chemical oxidation at combustion and halting of the combustion was shown in the familiar triangle in Figure 3.1. The two-dimensional triangle is aided with the expansion, explaining the combustion process. Thus, and all the sides of the fire of the triangle were intact in proper state, with the proportional burning took place. When any one of the sides was removed, burning would stop. Both of the introduction of the modern knowledge of the chemical fire extinguisher, there were only the methods of extinguishing fire aligned with closely with each of the leg of the fire triangle. Cooling the fire removed from the heat of the leg, excluding the oxygen from the fire removed from the oxygen leg, separating the fuel from the fire removed from the fuel leg. When chemical extinguisher agents were introduced successfully used with the fire extinguisher, additional information was required to explain each of the chemical. This new information added another dimensional to the diagram. The new diagram is known as the tetrahedron fire. It is the four-triangle surface that makes up a solid pyramid forming of the depth, and each of the triangle surface shown as an element necessary to continue the combustion. It shows the combustion fire is continuous chemical reaction with the change of the constantly based because of the external condition of the chemical extinguishing agent, potassium, sodium, bicarbonate type of dye-chemicals vaporizing liquid, inhibiting the chain of the reaction of the fire and interfering with or cutting off the conditions of the necessary for the combustion of those three parts of the fire triangle may represent the chain of the reaction prevented with the inhibiting of the chemical extinguishing agent or agents, which pulls out the flame. Figure 531 shows the fire triangle, the fuel, oxygen, and heat. Figure 5.2 shows the tetrahedron of fire, fuel, temperature, oxygen, agent, uninhibited chain reactions. 3.3. The basic definition of properties of fire. Ignition temperature. The ignition temperature is substance, solid, liquid, or the gas is the minimum temperature which the substance exposed to the air must be heated in order to initiate, causing the self-sustained combustion. Ignition temperatures of the same substance vary in accordance with the percentage of the combustion of the vapor gas mixture, shapes and sizes and spaces, whether the ignition occurs with the rate of the duration of the heat and the kind of the temperature, ignition source of the oxygen concentrated, other effects of the material that may present. Therefore, ignition of the temperature should be located with the approximation. Vapors in process, the combination of the gaseous substance given off the material with the burning of the burning wood. Heat causes the resinous substance in the wood vaporized. The vaporized combined with the oxygen in the air. The flame of the kindling of the ignites the combustible vapor oxygen gas. The heat from the fire overheats the wood, which in turn liberates more vapors, thus sustaining the fire until the wood is consumed. Vapor density. Vapor density is the term used to explain the weight of the vapor. When speaking of the weight of these vapors, they're usually compared to the air. Those vapors density of 1, therefore the substance vapor density of 1.5 or 1.1.5 times is heavier than air. It has such a vapor density of half of the weight of only half as much of the air. Figure 3.3 shows the density of the gasoline vapor demonstrated with a small three-rolled candle with a gasoline-soaked rag. A light of the candle is placed in the lower end of the trough. The gasoline-soaked rag placed in the upper end of the gasoline vapor. The heavier the air will flow down through the throw light candle as well will ignite. Flashback of the rag at the top of the throw with the insulation shown. The need for the no smoking within 100 feet signs displayed around gasoline storage areas. Flammable explosive limits in this case. Figure 3.3 shows the vapor density, the rag and the candle. The gas in the vapor with flammable mixtures with the air or oxygen, therefore minimum concentration of the vapor. The air below the flame does not occur with the vapor. Air mixture comes in contact with the source of ignition, thus into the lane to ignite. The most flammable vapors, gases, also have maximum proportion of the vapor gas in the air, which the flame does not occur too rich and to ignite. A few materials like ethanol oxide decompose and burn with no oxygen present. The flammable explosive range. The range of the combustible vapor gas or air mixture between the upper and lower flammable liquids known as the flammable range, explosive range. For example, the lower limit of the flammable and auxiliary acrylonitrile is ordinarily ambient temperatures at approximately 3% of the vapor and air volume. The upper limit of the flammability is 17%. That all the concentration of acrylonitrile vapor is air falling between 3 to 1.7% on the flammable explosive range. F. Flash point of the fire point. The flash point of the liquid, lowest temperature of liquid of which gives off the vapor sufficient to cause a flammable mixture with air near the surface of the liquid within the vessel. To use some of the solids, such as a camphor or naphthalene, changes solid to vapor for the ordinary with the room temperature. Therefore, the flash point will still in the solid state. The fire point, the lowest temperature in which the substance continues to burn in the air, is usually a few degrees above the flash point. 34. Principles of fire. Ignition and combustion. Fire and combustion may be described in the rapid oxidation with the action of the evolution of heat and light. The oxidation material type of the continuous long as it exposed to the oxidizing agent, which may be in air ambient temperatures. Oxidation usually slow, with the process noticeable with a human series. Example of such slow oxidation are resulting from the iron yellowing paper. As the temperature rises above the ambient, the rays of the oxidation becomes rapid and generates the heat. When the ignition temperature is raised, the flame appears. The ignition has been taken, and the combustion is in continuous burning that flows through against the ignition. After the ignition, fire. Actual burning fire is much more complicated with the chemical reaction than it is with the common explained with the fire triangle in Figure 3.1. Most recently, the tetrahydrogen fire in Figure 3.2. The temperature rises above the ambient pyrolysis. Take the pressure. The pyrolysis chemical decomposition of the material through the action of the heat is then proceeded through the following stages: decomposing combustible material slowly, giving off gases including water vapor, and combustible gases are not ignitable during the early stages of pyrolysis. Pyrolysis. Gas elevation continues. Some of the gas becoming ignitable as the temperature increases. The gas elevation evolution increases. The ignition temperatures has evolved. The gas is too rich. It is first the carbon dioxide water vapor to sustain the flame with a very large. However, the heat of the flame starts secondary pyrolysis. Reaction process flammable combustion occurs entirely. Gasoline dissipates vapor phases. The gas evolution may be also that it blankets the fuel surface excludes the air that prevents the char burning, retards penetration, the heating delay, the ignition temperatures and penetration deeper the combustible material. As temperature increases, the char begins to glow and the air flows to support combustibility. Combustion of the fuel in itself burns as well as the decomposing gas if the related released heat and concentrated sufficient to sustain oxidation. More heat generated with the loss of the convection, radiation positive heat balance exists. If, however, most of all the heat generated is lost, there is a negative heat balance. The fire goes out as the match flame is in the wind. As sometimes condition known as feedback may exist, the feedback is generated heat and prepares adjacent combustibility material for burning and raising ignition temperatures. The feedback is not adequate. The fire goes out. In addition, with the heat generation during the pyrolysis, the concentration of the oxidation agent is another factoring for determining whether the non-ignition combustion can occur. Therefore appears the minimum oxidation agent concerning concentration for all the materials below. The combustion will not take place. The exemption of later are some combustible solids, such as cellulose, nitrate, and contained with oxygen and constant molecules. The oxygen can be released with the heat of the even if there is no air supply. The pyrolysis reaction may take place with the presence of the air. Example: the charcoal in cooking ovens, which continue the oxidation, produces the minimal amount of air. Summary of principle of fire. The principle of fire may be summarized as follows. There must be an oxidizing agent, combustible material as source of ignition for the combustion to take place. 2. Combustible material must be heated to the ignition temperature before it will burn. 3. The combustion will continue until the combustion material is removed or consumed. B. The oxidization agent concentration or lower below the essential, and C. The combustible material is cooled below its ignition temperature. 3.5. Heat energy sources. Since fire prevention and establishment of the depending on the control of the heat energy, the essential for the firefighters know the common ways in the heat can be produced. The following discusses briefly the heat energy sources. A. Chemical heat energy. The source of heat resulting from the oxidation primarily concerning with the fire protection engineers. The following are the different ways the heat produced through the chemical process. Combustion. Combustion, the heat of the combustion quantity, the heat released during the oxidation substance fuel, the heat normally utilized in industry, domestic use, and is measured in the terms of the British thermal units. The heat intensity of oxidation, complete with the partial or almost all the compounds with the carbon, hydrogen, oxygen, depends on the oxygen consumed, but those heat produced with the combustion is limited by the air supply. 2. Spontaneous heat. Practically all the organic substances which are capable of combining with the oxygen will oxidize in some critical temperature. Evaluation of heat that is exposed to the atmosphere. The rate of oxidation normal temperature is usually slow in heat, which with the release of the transfer to its surroundings. This keeps the temperature down and prevents the ignition. This is not true for all combustible materials. Oxidation of some of the material generates the heat more rapidly than it can dissipate, which results in spontaneous combustion. Either enough air must be available to permit oxidation, yet not so much but the heat is carried away by the convection and as rapidly as formed. Oil rags might be heat spontaneously in a wastebasket, but would not do so if these rags were hung on a line where air movement is sufficient to remove the heat. Again, a tightly packed bale of rags is not likely to contain spontaneous combustion as a loose bale. Because of the many possible combustions of sub insulation, non-positive prediction can be made, but the material will be heat spontaneously. Fire safety engineers should not only be aware of possible spontaneous combustion fire caused by the oil rags, pipe or coal pipes, foam rubber, but also aware from the oxidation agricultural products can reduce fire spontaneous combustions. Grain, the large piles and bins and piles of grass, haze will oxidize the paint the ignition when saturated with a certain amount of moisture. Fires from this source may not be prevalent on the farms as in urban areas where agricultural produced products are stored. 3. Decomposition. The heat of the decomposition, heat released for the decomposition compounds such as cellulose nitrate make commercial, military, and explosive. 4. Solution. Heat of the solution is heated reduced with the substance dissolved with liquid. Most material released with dissolved chemicals such as concentrated sulfuric acid produce enough heat to dissolve with the dangerous, and the chemicals that react with the water release the heat are not combustible but liberated with sufficient heat and ignite the combustible material nearby. B. Electrical heat energy. Electrical heat energy produces heat with an electrical current flow through a conductor when a spark jumps as an air gap. Resistant. Electrical wire other than conductor electricity offers resistant, thus reduces the heat. The heat from these causes the oxidation, ignition, nearby combustible fire result. Fires of these types are quite common, although in all areas using electricity as a source of heat of energy. 2. Induction. When an alternating current is passed through the wire induces the current in another wire parallel to it, a form of heat called the induction heating is produced with the current carrying capacity of the second wire is inadequate. The inducing the heat is produced with the resistance of the flow of electricity. Molecular friction. An example of the latter is in the heat of the produced is in a microwave oven. 3. Dielectric. Dielectric heating is produced by the insulating material imperfect, therefore, or although allowing leakage of the current. This heats the insulating material, which may eventually ignite nearby combustible material. Arcing. Here from arcing occurs when electrical current which carries the current interpreted with the current leaps of the gap. The temperatures in the arc are very high and may ignite incombustible flammable material in the area. 6. Static electricity. Frictional electricity is electrical charge that accumulates on the surface of two materials that have been brought together with a separated. One surface becomes charged positively, the other negatively. In two objects are not bonded or grounded, they accumulate sufficient electricity to discharge the spark, and the spark produces the limit light heat, which will ignite the flame or vapors, gas, and clouds of combustible dust. 6. Lighting. Lighting is discharge of electrical charge on one cloud of the opposite charge to another cloud on the ground. Lightning develops very high temperatures and many material high resistance which may be in its path. C. Mechanical heat energy. Mechanical heat energy, especially friction heat, is responsible for the significant number of fires annually. A few are caused by the heat or energy released from the compression. 1. Friction heat is the result of the resistance of the motion of the two solids rubbing together with the intensity of the two depending upon the amount of mechanical energy transformed to heat and on the rate in which the heat is generated. 2. The heat of compression, the heat of the release with the gas compressed usually for the purpose of the ignition compressed the diesel engine, which needs no sparks for ignition. The fire may be caused by the direct of jet compressed air gas into the pipe. The air is converted to the heat and ignites in the oil film on the inside of the surface of the piping fittings. Nuclear heat energy. Nuclear heat energy is released from the nucleus of an atom. The nucleus is held together with a greater force, which can be released by the bombardment of the nucleus of the particles of energy. The bombardment, the fission and fusion releases the energy in the form of the tremendous heat and pressure. Also, nuclear radiations and nuclear fission energy is released by splitting the nucleuses. Nuclear fusion energy is released by the fusion of two nuclei. Nuclear weapon firefighting procedures are discussed in Chapter 6. 3.6. Classes of fire. Fire is divided in four main classes: Class A, B, and C, and D fires. These classes are based on the combustion characteristics of the ignition material and must be installation fires or combination of at least two or sometimes all these classes. Class A fires. Class A fires are fires of ordinarily combustible materials such as bedding, mattresses, dunnage, books, canvas, wood, papers. Class A fires must be dealt with by cooling the fire between and below the ignition temperature. All Class A fires leave embers which are likely to rekindle as the air becomes in contact with them. Therefore, a Class A fire must not be considered extinguished until the entire mass has been cooled thoroughly. Smothering is not effective for the Class A fire because there is not lower the temperature of the burning embers than below the surface of the fire. Class B fires. Class B fires are those which occur with the flammable substance of the gasoline, jet fuel, kerosene, oils, paints, turpentine, grease, and other combustible substances which do not leave embers or ashes. Class B fires can be extinguished by providing a barrier between the burning substance and the air and oxygen necessary for the combustion. Chemical foams and the mechanical foam procedures such as barriers are known as permanently smothering agents. Carbon dioxide is also a smoothing agent, but is effective only in temporary. The application must be renewed. Therefore, is in any danger of reignitions. Class C. The Class C fires are in live electrical materials. They present an extra hazard for the firefighter because of the danger of electricity shock. The non-conducting extinguishing agent is essential for the firefighting Class C fires. In additional consideration, class fighting C's, in fact, might be quite important to avoid damaging electrical equipment in the process of extinguishing fire. Electrical instrument and get contact with contaminated with the extinguisher agents except with the gases. First step of the extinguisher in Class C is secure the source of the power of the secure equipment on the fire. The preferred agent is the fighting with the Class C carbon dioxide and monobromotryl methane, since they give the protection against the electrical shock, are not likely to injure equipment. Water flogging, although not preferred, may not be used under ordinary conditions and not transmitted electricity with the fire together. It does not transmit electricity with the firefighter as well as solid stream water, but it will be damaged to the energized electrical equipment. Class D fires are those that combustible materials such as titanium, zirconium, sodium, potassium. The greatest hazard exists for those metals of the molten state in the infinitely divided forms. The trimming and the shavings are ordinarily extinguishing agent of the effectiveness of the metal fires. They are posed and controlled with the covering special dry powder with the granular materials which consume oxygen, which do not react with the combine adversely with the metal. Chapter 4: Tactics and Techniques of Firefighting.